Ladies and gentlemen, the opening ceremony will commence shortly. Please kindly mute your microphone for the smooth running of today's ceremony. Please be reminded that the QR code for the attendance will be available at the end of the session, and audiences are required to answer a few questions beforehand in order to get the e-certificates. Thank you. Please rise for our national anthem, Negaraku, and University Malaya anthem.
University Malaya, kebanggaan kita semua, bertambah para ilmuwan di berbagai lapangan. Kami bertekad hati mencapai cita murni, tradisi kecemerlangan menepati wawasan. Di sini kami sedia berbakti, terus berinovasi. Kami harapkan generasi muda, teras nusa dan bangsa. Varsity kesayanganku, sungguh banyak jasamu membentuk insan mulia, berilmu berbudaya. Di sini kami sedia berbakti, terus berinovasi. Kami harapkan generasi muda, teras nusa dan bangsa. Varsity kesayanganku, sungguh banyak jasamu membentuk insan mulia, berilmu berbudaya.
Please be seated. Now, we would like to invite Muhammad Farihin bin Azman to recite the Doa. As for non-Muslims, let's meditate for a minute.
الفاتحة. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على أشرف الأنبياء والمرسلين وعلى آله وأصحابه أجمعين. اللهم إنك خلاق العظيم، إنك سميع عليم، إنك غفور رحيم، إنك رب العرش العظيم، إنك البر الجواد الكريم. Ya Allah, Engkaulah yang mempunyai segala kepujian. Engkaulah yang berhak menerima segala kepujian. Engkaulah yang berhak menerima segala kesyukuran. Engkaulah yang memiliki segala pemerintahan. Di tangan Engkau segala kebajikan, kepada Engkaulah kembali segala urusan. Allahumma ya Karim ya Rahim, cucurilah rahmat dan rahimmu ke atas majlis yang kami adakan ini ya Allah. Berkatilah ia dari awal hingga ke akhirnya. Ya fa'alu lima yurid, kami juga memohon perlindungan daripadamu dari segala perkara yang boleh mencacat celakan majlis kami, dan daripada segala perkara yang melalaikan kami dari berbuat ketaatan kepadamu ya Allah. Kepadamu juga kami serah segala urusan kami. Rabbana alaika tawakkalna wa ilaika anabna wa ilaikal masir. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azaban nar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa ashabihi wa sallam, walhamdulillahi rabbil alamin.
Thank you, Farihin. A very good morning to distinguished guests, speakers, participants, ladies and gentlemen. Welcome to the opening ceremony of the Next Earth Virtual Conference. To get things started, we are pleased to invite Elian Mizati binti Muhammad Ismail, the director of Next Earth, to give her welcome speech. Please welcome.
Thank you, host Nikki Yohannes. First and foremost, I would like to express gratitude to our fellow lecturers and speakers. Secondly, I would like to thank all of our committee members for working hard in making this program a reality. And lastly, to all of you audience, I would like to welcome you and thank you for joining us today. Starting my speech exactly 3 years ago, on 14th of March 2018, we have lost one of our greatest minds in our era, Professor Stephen Hawking. What drives us to pick up theme Next Earth is because one of many Professor Hawking's last warning to humankind, which is, we must leave Earth to survive. It could be a new virus, climate change, nuclear war, the expansion of sun, artificial intelligence gone rogue, and many more causes that could annihilate the entire human species. But if this happens and the planet is irreversibly damaged, could we find shelter among the stars? We can and must use our curiosity and intelligence to look to the stars. We must do it now before humanity is taken by some disaster that we cannot control. One of the only solutions is to abandon the sinking ship and set course for new worlds where humans might not replicate their mistakes to ensure the survival of humankind. This would be one of the greatest hurdles for humans as a species need to face, searching for the next rocky planet with liquid water that could sustain life, and another 1001 factors that need to be taken to make sure we could live there and later colonize it. By date, after looking towards the heaven for more than 20 years, scientists has confirmed 4,000 exoplanets, and only few of them is within the star's habitable zone, where the temperature is just right for liquid water like our home, Earth. The closest exoplanet to us orbits Proxima Centauri, which located 4.2 light years away. If we use the fastest rocket we ever built by date, we will take thousands of years to reach it. Later in our session, Dr. Juan Carlos will explain to us the possible methods on how we could make interstellar travel a reality. Getting there would surely be hard, but colonizing it would be as hard as us wanting to terraform the planet, which later will be discussed by Dr. Kuhan Chandru from UKM. And all of this would be a far worse solution to resolve without touching the ethics of space travel. And this topic will be touched by Mr. Wan Muhammad Imran. For those who don't know, Mr. Wan Muhammad Imran is a good friend to Dr. Imran, our beloved lecturer in University Malaya Physics Department. For the survivability of humankind, I will now pass the stage to Nick Yohannis, our host. Thank you very much.
Thank you, Miss Ilian. Next, we are pleased to invite Dr. Goh Boon Tong, Associate Lecturer of Department of Physics, to give his opening speech and officiate our ceremony. Please welcome.
Thank you very much to the NC. So good morning to all, and good morning to Ilya Bizati as the Director of Virtual Conference 2021 Next Earth. And good morning to Mr. Jama, President of University Malaya Physics Associations, honorable speakers, respected audience. First of all, I welcome all of you to our novelties occasion today, Virtual Conference 2021 Next Earth. Pandemics has changed the way we organize programs like this. Although facing difficulties in adapting to a new normals, this concurrence it makes possible. I am thankful that we managed to bring this conference to life. We intend to spread knowledge, share information, and engage with society. This conference aims to expose the general public to the ideas of searching for a new home, Earth 2.0. It includes its challenges from different perspectives like physics, astrobiology, and others. Everything does not last forever. In the future, humankind will need to venture into interstellar civilizations. We need to find new exoplanets that can sustain life to call home. I am aware this somehow sounds like illusionary, but we need to keep in mind that science is weirder than fictions. Today, we are aiming to seek wisdoms. Our brilliant speakers who are experts in their fields will bring you to a dimension of thinking that maybe some of you have never thought existed. I believe simple acts such as sharing information can ignite interest and curiosity in our hearts. Every person in the audience possesses a great potential to create exceptional ideas, mind-blowing discovery, and develop new technology to drive our society to a higher level. Our progress starts not takes too much time to complete due to our current conditions. But we will try our best to make use of that time effectively, ensuring every second counts. I am overwhelmed with gratitude that our speakers are willing to spend their time with us and share their remarkable experience. I am convinced that the audience will learn a lot of beneficial comprehension from the sharing sections. Thank you again, dear speakers, for joining us. Lastly, I would like to thank to the organizing committee for their unparalleled dedications in realizing this conference. Thank you to the participants for joining the event today with an eager spirit to give new knowledge. I hope this conference will be a kickstarter to more beneficial program in the future. We must always try to give the public's different point of views in seeing our work. I hope you will find this virtual conference to be a place that offers excitements, encouragements, and explorations. Therefore, I here officially officiate the opening ceremony of the virtual conference. Thank you so much and stay safe and stay blessed.
Thank you, Dr. Govuntong. We have now come to a very important part of today's ceremony. We would like to invite our first speaker, Dr. Juan Carlos Agaba Marcos from Department of Physics, University Malaya. Before proceeding, here's a brief about his education and work background. He started his education in Bachelor of Physics at Universidad de Valencia, Spain. Then he continued his PhD in astrophysics at University College Cork, Ireland. He started working as a postdoctoral fellow at Academia Sinica, Institute of Astronomy and Physics, Taiwan from 2011 till 2014. Then, from 2014 till 2017, he continued to be a postdoctoral fellow at Korean Astronomy and Space Science Institute, Korea, and soon moved to Seoul National University from 2017 till 2018. From 2019 until today, he is now a senior lecturer at University Malaya. Without wasting any time, please welcome Dr. Juan Carlos with his talk, Fancy a Weekend Trip to Proxima Centauri? How to Make Interstellar Travel a Reality. If you have any questions, please leave your inquiries in the chat box and our speaker will get through that later. This speech session will be recorded and shared to the audience later. Please welcome Dr. Juan Carlos.
Hello, good morning. Okay, I suppose you can see my presentation, right? Okay, so let's get started. Good morning and thank you very much to the organizers to give me the opportunity to participate in the Next Earth virtual conference under the Perfume program. Today I'm going to divide my talk into different various sections. First, I'm going to give you an introduction of what are the problems of interstellar travel, what is our current understanding, what is our current standing point in interstellar travel, and what difficulties we are facing. I will discuss then what are the possibilities both in the near and the distant future to address faster than light traveling. And I hope after that I can wrap the conclusions and give you the key points and ideas so that you have all these valid points that you can take home. Okay, we humans have started as a nomad species. At the original times of our species, we used to travel and discover new countries. And some people in different countries, for example in Mongolia, are still mostly nomads. And even though right now we have become a species that prefer to settle down in a particular location, it is very natural still to travel among different places and different locations. whether it is for touristic reasons, because we want to look at new places, we want to see new things, we want to discover new cultures, or for working purposes. Just, I think I'm a good example of working because of working reasons, and also because of discovering different places. Well, we still have this sense of adventure, of discovery, on finding out what is beyond the locations and places that we can reach every day. So we are always going to be looking for which ways we can actually reach farther distances, which ways we can go faster to these places, and we are looking for what is going to be the most convenient method of transportation. For centuries, this has been only on foot, or we were typically stuck on using as maximum horses or other animals, and transportation would be basically done on carriages. However, with the Industrial Revolution in the 18th century, we had a new myriad of locomotions, such as, for example, the train that became available, which gave us new ways and new perspectives for traveling and transportation. As an interesting note, critics of the early steam sweeping locomotives were considering the dangers of those terrible accelerations and speeds. Some of them were claiming that when we would go at 80 kilometers per hour, body parts of people would actually just fly away from our bodies. Others even suspected that the human body would not be able to stand these high speeds, and the body simply would melt at high speeds. Of course, today we know that this is not really the case, and that when we are traveling at different speeds, we don't know if we are traveling or the rest of the world is traveling away still, as relativity says. And the most important topic that we have to take into consideration is not speed, but acceleration. Of course, accelerations can be an issue for our body, but not accelerations that they were considered at that point. So far, we know our limits and we are going to be safe with these speeds. A new revolution came in the sense of traveling with the first flight of the Wright Flyer, which was the first successful heavier-than-air powered aircraft. With this air model, the Wright brothers were able to fly about 6 kilometers in a flight that marked what today is considered to be the beginning of the pioneering era in aviation. You know, from the first flight to 6 kilometers, everything evolved very rapidly. And nowadays, we have commercial airplanes that can cover distances of about 20,000 kilometers. The planes can fly for more than 20 hours non-stop. And if we consider that we can fuel those planes, they can even reach days and days without touching the ground. And that's even considering that we are not taking into account supersonic flights. You know that some years ago we had the Concorde, who could travel to supersonic distances. So it could reach much higher speed than the speed of the sound. But it just became a bit out of the game because the cost benefits was not practical. The next step came, unfortunately, from the side of war and warfare, from the ballistic ideas. In the race to make long-range missiles more effective and more deadly, the V-2 was developed in Germany during the World War II, and that became the first artificial object in travel that crossed space, going beyond the Kármán line. This is the line that we define as what is the boundary between Earth's atmosphere and space in 1944. On the positive side, let's forget this is because of warfare. But this was showing everyone, showing humanity, that we could use the rockets and launches to be able to do some development towards space. And this indeed was crucial in the development of space race that would culminate, as you know, with the landing of Apollo 11 on the moon, and Neil Armstrong as the first human who was stepping on a different world in 1969. As you know, his very famous words were, "This is a small step for a human, but a huge step for humanity." Once humanity has reached the moon, a different world that is not Earth anymore, of course, it seems pretty straightforward that the next step, the next frontier is space. This table here summarizes the greatest achievements in the human race so far, from the V2 rocket towards Sputnik, that were the first artificial satellite, Vostok 1, that put Yuri Gagarin as the first human in space, of course, soft landing in the moon, the first human in stepping in a different world. Coming towards recent years, we have the Mars Pathfinder, who was the first operational rover on Mars, not just the moon, but we are actually going much farther away, reaching other planets of Mars. And in August 2012, we had the Voyager, who was the first object reaching the interstellar medium, which is the region that we consider beyond the influence of the solar wind. So we are almost reaching the outer regions of the solar system. In November 2014, we had the first landing in a comet. In this case, was the 67P Churyumov-Gerasimenko. And in January 2019, just a couple of years ago, we had the New Horizons. That was the first probe that was passing by and taking pictures of Pluto. And after that, it was even going beyond, and that was the first probe reaching Kuiper objects. In this case, we were taking pictures of the Ultima Thule, which we think is one of the remnants of the formation of the solar system, also in the boundaries of it else. So what do we make out of this table? Well, technically, based on the latest lines of this, we can say that we have already dominated interstellar travel. We have a Voyager that is really going outside the solar system, and the same with the New Horizons. So we are capable of sending probes to Mars, landing in a surface of a different world, visit Pluto, going outside of the boundaries of the solar system and beyond this. In this sense, I would say that we have probes that are already traveling in space. They are already leading towards the cosmos. And of course, if they were directed in the proper direction, they would eventually reach the nearest or nearby stars. So in this sense, really, I would say we are already in the interstellar traveling area. It's just a matter of practicality. It is just saying that we need time to reach it. We need to be more practical about it. So the question is, how can we do this? Well, if we want to know how we can really make it practical, how can make it better to travel to the nearest stars, the first thing that we have to know is how far are they? In this map, I am showing the nearest stars to the Sun, the closest neighbors that live with us. And we can see that the closest star is the system of Alpha Centauri, with a triplet of stars. The nearest of them is Proxima Centauri, which is located at a distance of about 4.24 light years. Remember that a light year is the distance that light travels in 1 year. This is so that you can make an idea of yourself, 4 orders of magnitude, that is 4,000 times larger than the distance from Pluto. So you can imagine how much light needs to travel from Earth or to the Sun from to Pluto. Multiply that by 4,000 times, that's a light year. And multiply that by 4 again, and that's how close the next star is. What about the other stars? Well, fortunately, we have about 7 stars that are around the same distance, less than 10 light years. But of course, if we don't want to be restricted only to these stars, we are going to be thinking about distances beyond 10 light years. Or, of course, if we want to go even farther than that, we have to start really thinking big. So it is not a matter of just traveling to the next star. We really have to figure out how to take into account these larger distances. So here's the question. How can we do this for our purposes? Let's take into account, for example, what we have reached so far. The Voyager are traveling at speeds of about 15 to 17 kilometers per second. However, Voyager are not the fastest probes that we have sent so far. The record for this is the Parker Solar Probe that can reach speeds of 70 kilometers per second. Again, compare this with the typical speed of your car, which may be about 70 kilometers per hour. So that's 3,600 times slower than the probe. Even if we consider typical speed cruises, like when you go to the Boeing 747, for example, the typical speeds are about 0.3 kilometers per second. This is still very much far away from the 70 kilometers per second. So this is a really a huge speed for our everyday life. However, even if we consider this, the Voyager would need 75,000 years to reach the nearest star. And even the Parker Solar Probe would need 20,000 years to reach Proxima Centauri. Well, with these numbers in mind, I think Proxima Centauri is not going to be your first idea when you're thinking about a weekend trip. At least if you want to make it back to work on Monday, I suppose. Well, that's for the time being. So we have to improve this side here. Not only that, but also the question of power arises here. How much power do we need to launch a rocket and give it enough acceleration and enough speed so we can travel at a reasonable speed, like the ones I was mentioning for Voyager or the Parker Solar Probe? Well, I'm going to give you some numbers. If you want to accelerate 1 ton of material to 1/10 of the speed of light, you need about the same energy that is consumed on the whole Earth in 1 year. Well, it seems that we have to do better than that, right? But this is only one of our concerns at the point. The environment can be an issue because we have gas and dust that can damage the spaceship, and we have interstellar radiation that can be lethal for astronauts. And last but not least, there is a question of, again, practicality, or let's say technology, that arises when we are considering when to launch a mission. Let's say you know, and this is something really nice, that technology is getting better and better as we get to new years. So if you consider about what is the technology we have today, what is the technology we are going to have in few years? So maybe if we launch a mission today, it may get overtaken by future missions that are launched in the future that have the technology. So from this point of view, isn't it better if we just sit and wait for the technology to improve and then everything will be better in the future for this matter? Well, let's think about this. We have to consider three important ideas here that are engaging each other. When we think about space exploration, of course, it's not only a matter of science, a matter of what can we do from the science point of view, but this is an interplay between different aspects. I already mentioned one. It's not what we can do today, it is what is beneficial or more useful and more practical in the long term. How does it work? Once we have the scientific basics, we need to consider about how we can engineer the solutions. Or put in a different way, how can we transform the physical ideas into models that are something tangible? How is this going to work? For example, at the beginning, we knew about how we can have some kind of magnet, make it spin to obtain electricity. So, from the physical point of view, we know that we can use electricity to make a motor. But then, of course, this is the physics point of view. From the engineering point of view, how can we make from a motor based on electricity to electric cars? This is a very different point, right? We have to take this physical principle and make it into something tangible, into something real, and into something practical. And of course, we are always considering that we have an economic interest. Right? For a proper space exploration, for a next real trip to the next Earth, we need a synergy between all these different milestones. But keep in mind that the precursor of all of them, the original seed, the point that is our zero starting slot, is the scientific background. If we don't have the physics, if we don't have the basic scientific ideas, then we cannot move forward. This is where we are starting, and this is the machinery, and this is the engine that is going to be moving all the wheels so that we can keep moving forward. And since I'm a physicist, let me, of course, say that I'm a bit biased towards the physical side. I am not an engineer, I'm not an economist, so allow me for the next slides that I focus on the physical point of view. Let's consider, based on this idea, the problem of interstellar travel from the science point of view. Currently, what we have is that we are basing our space exploration on either solid or liquid fuels. We know that we have the rocket science here, which is not really rocket science, it's not that difficult, but we have two big problems with the current status. Number one is the amount of energy that we can obtain by burning fuel. It's really low. You have to consider that this is just chemical reactions on the game. And chemical reactions are, relatively speaking, quite an inefficient way to obtain energy. Second problem is we need to store the fuel in the rocket, and this is going to be adding weight to the rocket, correct? And you will need, of course, extra fuel to push this extra weight. And then you will be adding even more weight, which will need more fuel to keep pushing this. And you know this is one of the biggest problems that we have in rockets today. As a result of all these issues, what we find is that the total payload that we can actually put in a rocket is going to be maximum of about 3% of the total weight. It is not good, it is not great, but that's what we can do so far. On top of that, think that only recently we are able to recover the different stages of the rockets with, for example, projects by Elon Musk and SpaceX and these kind of ideas. So we are still starting to develop about how we can make this more and more efficient. But worry not. Science comes to the rescue. And of course, there will be new ideas and new methods that we will soon be improving the situation that we have so far. So please come with me and let's explore what are these kind of situations and new ideas and new methods. One of the methods that we can propose as a near future solutions is the ion propulsion. The idea is that what we can do is produce ions. These ions are going to be charged. So what we can do is put some sort of magnetic field around so that we can work with them using instead of pushing them with reactions, we can push them with electric and magnetic fields. So what we are going to be doing is that if we design this in a smart way, then we can push these ions and we can launch them at a very high speed and then use this high speed to be able to push our space ship. The problem, the issue that we have so far is that the ion engines produce very little thrust. So, you know, if we want to make a race with nice cars, and you know, we want to accelerate from 0 to 100 kilometers per hour. With the ion propulsion, we can accelerate from 0 to 100 in 4 days. Well, not so good in terms of acceleration, not efficient, but we can accelerate very much long after any chemical engines would have run out. We can keep accelerating and keep accelerating many days after we would have any other kind of fuel. So this is a very good thing. NASA Space Glenn Center is working now on a new generation of ion-propulsed engines that may be able to produce more power, more thrust, and more acceleration. And it will be working continuously for several years. So if you are interested, you can go for NASA Glenn Space Center website. You can check ion engines and check the latest updates on this solution. Another idea that we have as a near future solution is the use of solar cells. The idea behind solar cells is that lights are made of photons, and we have found that light has momentum. Then, if we have momentum, we can apply this momentum of an object and we can make a force on that object. With this, we can think about we can have a sail or a large amount of material that is capturing all the light and is getting pushed by these photons. Of course, what we need to do is having a very large and extended amount of material so that we can collect as many photons as possible. So we need something really big for this. And at the same time, we need to be very light, because of course, when the more weight it has, the less is going to be pulled by this force. Something that is very big and very light, that's where the sail idea comes into the game. And of course, if we want to make it even more efficient, what we can consider is what is the material that should be making this sail. One option would be using the carbon nanotubes or similar possibilities. So it seems like a bit of a crazy idea, but we can think that this is already in the mind of many people. The sails, of course, will be only useful when we are nearby a source of light. So many people think that this is going to be suitable only within the region of the solar system. And of course, as before, the acceleration is not going to be too large as the ion propulsion, but at the same time, the acceleration can work out as long as you need. As long as we have some source of light, as long as we have the sun nearby, this can be accelerating. And we don't need any motor for that. The only thing that we are going to be needing is the sail. So no fuel required, which is very good for our aspects. This is already working. We have the prototype of one of these solar sails called Icarus that has been launched by JAXA, the Japanese Space Agency, in 2010. It has been tested, and so far the results are very encouraging. Again, you can visit the JAXA website and find what are the latest updates of this near future, already here solution. Let's leave the chemical reactions on a side right now. We already mentioned that chemical reactions are kind of very inefficient. And we have to think about what is the next step that we can work on if we need to have any of the motors or any of the fuel here. Of course, the next step is going to be using nuclear reactions, whether this is fusion or fission engines. If we break apart the nuclei of 1 gram of uranium, this is going to be generating 1 million times more energy than burning fuel in a chemical reaction. So you can imagine how much better having this kind of fuel or having this kind of engine is going to be for our space rockets. So I would say it really makes sense that we just remove the chemical engine from our rockets, and instead we put a nuclear engine on board. This has already been thought in many science fiction novels. If you've considered about Isaac Asimov stories or other authors, many of them were thinking about having a nuclear reaction on board. However, the big trouble is that with our current technology, the nuclear reactors, especially if we want to have them in a safe environment for the rest of the passengers of the space rocket, are still very large. And it's very challenging to be able to fit a nuclear reactor, small and safe enough in a space rocket with our current technology. So far, it is beyond our current technology, but of course, we already know we have this option. It will be a matter of how we can solve this technical issue. So in that sense, this is not a question of physics, not a question of how we can think about this. It's more an engineer question. And of course, I would say this is still a near future solution in the sense that as soon as we find how to engineer this, we can immediately get spaceships with a nuclear reaction inside. We can go beyond that. As you know, nuclear reactions are not the ultimate source of energy. We can also obtain energy with a matter-antimatter motor. You know that when we have antimatter and we put it in contact with matter, it would annihilate completely, converting all the mass that we had there 100% into energy. So this is going to be the most efficient way to convert mass into energy. But in this case, what we have is, again, two concerns here. One is that the total amount of antimatter that we have created so far is about just 50 nanograms. And this is probably not enough to have a lot of energy. We have to create and store a lot more of this antimatter. And that is the second problem, how to store the antimatter. Because so far, with the technology we have, we are able to store just a few dozens of particles of antimatter. So we need to improve this technology. We have to be able to use the nuclear and particle physics in a smarter way, in a practical way. On the bright side, as we have seen, the technology, not only for the matter, for the antimatter, for the nuclear reactors, for the solar cells, all the technology is already here. The only thing that we have to do is testing them, making new ideas, and have the proper engineering time to be able to find the solutions to the problems. And as we have mentioned, these technologies will be of very nice, useful terms for space travel. So we are here, we know what to do, we know what is working on, we just need the next step in the engineering side to be able to have all this technology at our proper use. All right, now let's think about this. We have a problem here, and it's that no matter how well we improve the technologies we have been talking about, there is always a problem that so far we have left behind. We have been saying, yes, we can accelerate, and even the acceleration is small, we can accelerate for a long time. Or maybe with nuclear reactors or antimatter reactors, we can accelerate much faster, and we can reach high velocities. But we have a speed limit. We cannot travel at a speed faster than the speed of light, 300,000 kilometers per second. And this is a limitation that is given by Einstein's special relativity. Of course, the light is something that, by law, cannot be surpassed in the universe. So, if we know about this, we still need years or maybe decades to reach the closest stars, and maybe centuries to reach other stars in our neighborhood, because we cannot go faster than this speed, and those stars are already light years away from us. The good news for this is that even if we need all these years, because special relativity effects, for example, time dilation and time contraction, the delay will be much faster for the travelers on board. So even if we think we need decades or centuries, the time will go much slower for the people inside the space rocket, and maybe from their point of view, it's only few years. So with this in mind, it seems that it's not going to be that of a barrier. And since we humans are explorers by nature, I really think that even with this limitation, this is not going to be a big issue. We will be able to just go beyond and reach the stars not so long in the future. Of course, the question here is, shall we be happy with this? Shall we just think that is our limitation? Can we do better? And typical thing that we humans do is, if we cannot adapt to the environment, can we change it? Let's think about this. Instead of traveling through the space-time and having the limitation of the speed of light, can we instead manipulate the space-time itself and accommodate it to our needs? I would say the big jump in interstellar travel will happen when we can surpass the limitations of special relativity and go towards general relativity, playing with the space-time, blending it, molding it to our needs, and having more fundamental knowledge on how to use it and be able to travel within the space-time. Question, of course, is how do we change the space-time to suit our needs? Can we really go beyond the limitations of special relativity and dream with devices traveling faster than light? Can we really bring to reality all these texts that are from the science fiction, like wormholes, stargates, warp drives, hyperspace motors? How is this possible? Can we really think about this? Let's go thinking a bit of this. I suppose you are familiar with the typical image of a wormhole. Typically, you will have something like a black hole, this kind of really special, a particular object that relativity predicts. And we have proof that they actually exist in the real universe. Like a couple of years ago, we have pictures, the first image of a black hole. What is a black hole itself? It's just a region that has so much mass, and it's so dense that the space-time based on relativity blends around it in such a really critical way that the space-time itself creates some sort of a singularity. It blends so much that it may kind of break the space-time itself. We know what is a black hole. What is a wormhole? The typical idea would be, well, you have this kind of point in which space-time is breaking. But what about if it just doesn't really break? What about if instead it just makes some sort of throat, and that throat connects to another hole so that it's connecting two regions of the universe that in principle are very far away? Well, this is the classic idea of wormholes here. Question is, of course, can wormholes, as we know it, really help us with interstellar travel? Can we enter a wormhole, then go through the throat and exit the other region and make this kind of interstellar travel? The first idea of wormholes actually comes back to Einstein and Rosen in a paper that they make together in 1935. The concept came back in 1960s again, but then Fuller and Wheeler realized that this kind of wormholes is unstable. What happens here is that the throat that we have will collapse very rapidly. They are so unstable that even before a single ray of light can go through them, they will already collapse into normal black holes. So this is not good for human transportation, right? So what happens is that when they transform into a black hole, of course, it will become a region with an event horizon, and if somebody is trying to travel there, they will get stuck forever, trapped inside the event horizon. And from any outsider point of view, of course, it will take infinite time to even reach that region. Let's not talk about going through any region and trying to go outside the black hole. So if you fall into this kind of wormhole, a big problem for you, you will not be traveling to another region of space. What you're going to be doing is just falling into there and get trapped forever. Of course, when you think about that, you will never be able to escape. So in practical terms, for humans, this is what we call a non-traversable black hole or non-traversable wormhole. So what is our hope now? Well, in 1980, Kip Thorne, who got recently a Nobel Prize, got a phone call from Carl Sagan, who was writing a science fiction book called Contact, later a motion picture starring Judy Foster. And Sagan really wanted to make a really believable way for his characters to travel across the galaxy using some sort of space travel shortcut. Spoiler alert for the movie if you hadn't watched it. Well, in the novel, initially Sagan was thinking about what if I use some sort of wormhole and then the characters travel through this wormhole. But Thorne really pointed to Sagan that in general this kind of wormholes would be non-traversable and maybe they wouldn't be able to use this. So, well, sorry about that. That's not the way you can send people to other parts of the galaxy. But still, that got Kip Thorne thinking about this. Like, okay, I said that black holes are non-traversable, but is this any way to figure out how to create a traversable wormhole? Well, the idea is that typically what you do with Einstein equation, which you see here on the left side here, is that you have the part of the matter and the part of the glass. The matter how much the matter is there is affecting the glass part, which is the continuum of the space-time. The amount of matter is affecting the curvature and the symmetry and the structure of the space-time itself. And at the same time, the structure of the space-time is telling how the matter is moving. So basically, this is what Einstein equations are telling us. What is the relationship between those two objects? Typically, what people have been doing was, I know how much matter I have. I know, for example, that I have this particular amount of mass. So how is this mass affecting the structure of the space-time? If I have this mass, how is gravity affecting anything else? This is the typical question that we are making. But at some point, Kip Thorne and his student Morris were thinking about, let's think the other way around. If we really want to know how to make a transversable wormhole that humans could use, we know exactly what we need. We know more or less what is the structure of the space-time that we need. So let's go the other way around. Let's go towards the Einstein equations, the reversal way. We know the right side. Let's figure out what is the structure of the matter, how we can put matter together in order to obtain the result, the wormhole that we want. So they were working on this, and they obtained the matter energy distribution that would give rise to a very nice, transversable, usable wormhole. A mathematical solution was really actually found. So yeah, we can do this. Like, there is a mathematical solution. But be careful about this. Because, for example, if I tell you, I have a sister that is 1/3 of my age minus 10. This is the typical equation that you do in maths. You can calculate an answer, but the answer is going to be negative. Yes, it is a solution there, but it doesn't make sense that my sister has negative age. So here the question is, for the wormhole, Kip Thorne and Morris found a solution. Question, does it make sense? Is it physically plausible? What is the case for this Einstein solution? Is the distribution of matter really reasonable? Well, the solution that they found had some stuff that they needed to create this kind of wormhole. And the problem that we found is that they violated what we call the weak energy condition. What is this? Basically, the idea that they are saying is that the mass energy is going to be negative, at least seen by some observers. So it's something like having some sort of a negative mass, something like that. So they dubbed this some sort of exotic matter. What is this exotic matter? I'm going to be using the term negative energy here a lot, but this is just a short form of discussing what is this exotic matter. Because negative energy is something that we can find every day. We have a potential energy. If we select the origin of coordinates in a normal way, this can be negative, so it's not really a big issue about that. The concern that we are discussing here is that the energy and the mass that we have is going to be negative. How do we understand this? Well, it's kind of reasonable here. Let's say we have this kind of wormhole. When we are at the exit throat, at the exit side of the wormhole, what is going to happen is that you, or rather maybe the space-time around you, is pushing away from the wormhole. You are going away from the center, you are going away from the throat towards the normal space. This is pushing you away, which is kind of, this is exactly what gravity should not be doing. Normally gravity is pushing you down, is attracting you. This is kind of repelling you. So is it like we have some sort of anti-gravity? Something like you have the reverse of what you would expect from gravity? It's something like if you have some sort of negative mass to be pulled away. So in that sense, in the sense of some sort of negative mass and gravity working the other way around, this is where we come up with the concept of negative energy. It just works the other way around. We have something that is working reversal. But of course, it's really strange. It's something that we cannot really imagine. We haven't found anything like this. Well, we will discuss about this later. So the thing is, what is this? This is something that we don't find in our everyday life, something that the more mass it has, the more it just pushes me away. Do we have any idea of any hints about something like this? Is it something that exists around here? And if it exists, how we can obtain it, how we can actually use it? Well, there is some effect, that is the Casimir effect, which is going to give us some hints about this. In classical physics, of course, you know that negative energy is not going to work, because in the sense that we are discussing this, is something that if we have nothing at all, this is going to be less than nothing. In classical physics, you cannot have less than nothing. But what happens if we go to the quantum realm? Well, in quantum physics, there is no such thing as nothing. Even if we are in the vacuum, in empty space, you will still have these quantum fluctuations, waves and particles appearing and vanishing all the time. This is basically the uncertainty principle in quantum physics. And of course, even though these vacuum fluctuations have an effectively zero energy, this is what we call the zero energy point, the idea is that you still have them. You still have some positive and negative, and they are kind of still going around there. But now let's think about this. Let's put two plates, two parallel plates there, close enough, close together, so that we can start feeling all the quantum effects there. What is going to happen is that typically radiation or energy or this kind of ideas will be given by waves. You know, like even particles can be considered as waves, and energy can be transferred by waves. And depending on what is the wavelength or the frequency of these waves, we are going to have one energy or the other, right? But if we put two plates together, what is going to happen is that we cannot have inside the plates waves that are longer than the distance between the plates. What is the meaning of this? The energy associated with that kind of waves cannot exist anymore, because the waves themselves do not exist, which means that we have to remove all these waves from all these quantum fluctuations. As a result, we are removing something from nothing. We have all these quantum fluctuations of the empty space of the nothing, and we are removing something from there. What is going on here? We are having less energy than the 0 point. So in some sense, you can think that this is some sort of negative energy, this kind of energy we are looking for. So indeed, theoretical physicists like Kip Thorne and other people are thinking that the Casimir effect is a potential source of negative energy, this kind of energy that we really need to create this kind of wormholes. And if we can actually take this and use it, maybe we can keep the wormhole open, make it transversable, and really use it for human traveling. Well, on the other side, we have also Malzavena, who is a physicist in the School of Natural Science in the Institute of Advanced Studies in Princeton. And he thinks also that if we can have this negative energy, this can support the existence of stable wormholes. And then we will have a bridge between 2 points in space-time that would not collapse before people have the chance to transverse it. Maldacena was, of course, making calculations much farther and was going deeper into the details. And he found that, well, since we are talking about quantum mechanics, typically what is going to happen is that the bridge between the two black holes is also going to be in quantum size. It's going to be basically microscopic. So it can only exist for very small distances. You would say, well, okay, if we have kind of a wormhole to travel for a meter or centimeters or microns, it's useless. Come on, we want something more practical. So if we want for humans to actually use proper wormholes, they have to be larger. And in some sense, if we want to make them macroscopic, we have to go beyond the physics that we know. There is something interesting. There is a theory that is the random Sundrum 5D theory that was proposed by these two people a few years ago to solve a hierarchical problem in particle physics several years ago. What was this problem? Basically, you know that we have the four forces of nature, and we have the strong, the weak, the electromagnetic, and the gravity. The three forces, the strong, the weak, and the electromagnetic, are kind of pretty much strong, and we can put them together. We can study particle physics considering these three forces, but gravity itself is kind of a weird kind of force, and it's by comparison really, really, really weak. So the idea of this model was that maybe the gravity is so weak in our three-dimensional vision of the universe. Four-dimensional if we consider general relativity and we plug time in there. So what happens if we have instead 5 dimensions, and what's going on is that the gravity is leaking through all this extra dimension that we have there, and that's why it's so weak? Well, it is a model, and the interesting part here is that Maldacena was considering what would be the implications of this idea for interstellar travel. What would be a wormhole if we can use this idea? Maybe we can just plug the throats using this extra dimension. May it work? Well, in a study by Maldacena, actually in November last year, he argues that if this model is true, then intermediate size, as like human-sized charged wormholes could actually be created. And these wormholes, maybe we could use them as a shortcut between two different times in space-time. Well, his calculations were showing that if you look at the wormholes from outside, they would still need a large amount of time to be traveled. But again, for people who are actually using the wormhole, for the astronauts that are going through it, then it will be very quick because of the time dilation effects. We are not talking anymore about going at faster speed. We are talking about using wormholes. So, in words of Maldacena himself, if we are traveling a distance of 10,000 light years, an observer who doesn't go through the wormhole and stays outside, of course, would see that they need more than 10,000 light years. But for the astronauts going inside, it will take just seconds to travel through the wormhole. Plus, it is the wormhole, the one that is attracting the astronauts to go inside and pulling the astronauts to go outside. So this will be done without any fuel at all. Only the gravity will be the one accelerating and then decelerating the spaceship. So this is fantastic. A potential traveler only has to be careful about the wormhole tidal forces and just making sure that no strange particles are coming into the throat to make the wormhole unstable. And once we consider these sort of things, well, we can use the wormhole. Wow. Of course, there is a big problem. As I mentioned, one of the things is there may be particles coming inside the wormhole. The particles may make it unstable. And if you are inside the wormhole when it becomes unstable again, goodbye to you. So it's really nice, it's possible, it's a viable method, But so far, as we know, it's maybe not the safest one. So let's make another question. Is there any safer alternative to wormholes? Can we think about some other method to play with space-time to actually be able to do interstellar travel? Well, let's go into the realm of warp drives. In 1994, the Mexican physicist Miguel Alcubierre proposed a method of stretching space in a wave that would basically, in theory, cause the fabric of space ahead of the spacecraft to get shorter and the space behind to expand. All right, so just imagine something like this. Whatever space you have in front of you is contracting, and you just pass through it. The space that is behind you is expanding and coming back to normal. So if you are in a wave like this, the ship in which you are will be riding this wave, and the center of this region will be just a space flat, so you will be kind of safe, not really feeling any of the tidal forces of distorted space-time. So this will be what we call the warp bubble in a flat space-time. What is the idea? Well, the passengers can be sitting peacefully without feeling any distortion, any tidal forces, any gravitational pull of the walls of the bubble. But as space-time contracts and expands on the front and the rear, then what is going on is that this bubble is actually traveling around the space itself. All right? And since it is not us, it is not the space that is traveling, it is the space-time itself, the one that is moving, then we do not have these limitations for relativity, telling we cannot travel faster than light. This limitation does not affect space-time fabric itself. So in principle, we could just create this bubble, make the bubble so that it travels faster than light, and we are just sitting in the middle of the bubble, peacefully traveling there and going to a far away distance in space-time. Also, this method is really in agreement with general relativity, as I said, because it doesn't really destroy any idea of relativity itself. We are just sitting, we are following all the rules, we are following all the equations, so it's a really way for transportation. Because the basic idea is the object that is traveling there, it is still slower than light. Our spaceship is not going faster than light speed. It's just sitting in a flat time. It could be stopped according to the local reference frame. So in that sense, we are not destroying any physical law. So it could be a way to actually transport. Okay, so this geometry exists. This is an idea that Alcubierre discussed. Now the question is, well, let's think about that. By the way, I have a small movie about how would it look like for people to actually see. And Earth is not being destroyed in this movie. It is just like because of the distortion of space-time, how it would look like if there is a space drive moving around Earth. All right? So if at some point you have some astronaut who is on the moon and is looking at Earth, and they see the Earth doing something like this, I'm going to show the movie again. If you see something like the Earth doing like this, it's not the Earth is destroying. It's just that warp drive cross between Earth and the moon. This is how it would look like for somebody who is away from Earth. It is basically like a lens distorting what we see. Okay, so how do we do these kind of things? Well, again, creating a warp drive is not an easy piece of work. It's much harder than it sounds. You have to have a huge amount of energy. To create all this deformation needed of the space-time, you need a lot of material. In principle, at the beginning of the calculations, Alcubierre was considering how much energy do we need, like maybe the energy of the sun or something like that, or even the energy stored in the whole galaxy. But there is an even bigger problem than that. It's not how much energy we need. Biggest concern is its negative energy. So that's a huge problem so far. Later on, however, José Natario, associate professor in mathematics in Instituto Superior Técnico de University of Lisbon, proved mathematically that any form of warp drive requires negative energy. So we can go around this. We are going to be needing this negative energy no matter what. The question, however, is he said we need negative energy. He didn't mention how much. And this can actually be changing because there are different models in which, even though the initial Alcubierre's idea was needing a tremendous amount of energy, Dr. Harold White suggested that if we consider a particular structure or a particular deformation or a particular shape for this warp drive, different amounts of energy are required. For example, if we have some sort of spherical or oblong shape for the warp drive, we can reduce the amount of energy to more reasonable amounts, something like maybe the mass of Jupiter or some tons, which is much, much better. It is still negative energy, but like if you tell me some tons, it's much better than if you tell me the mass of the sun, right? So, of course, the basic idea would be how can I work around, like making the shape of this warp drive bubble so that less energy is needed and it's more efficient. If we have a oblong shape, probably it seems to be better. Maybe that's why the Star Trek USS Enterprise was having this kind of round shape. Well, what we know for sure is that an elongated shape is going to use a lot of energy, so maybe the designers of the air carriers and the airplanes that make these long air flights are going to double think their work, and they are going to have to redesign their flights. So maybe passengers will have to sit in parallel. Well, Nathaniel believes that even a greater problem with the concept of the Alcubierre drive is present there, like other than how much negative energy we need to have. And this is coming because of the limitations of information. Imagine, for example, that we have a supersonic aircraft like the Concorde we were discussing before that is traveling at faster than the speed of sound. The issue is that it's traveling faster, so you don't hear the aircraft until it has arrived, correct? So the sound waves cannot keep up with the plane itself. So the same thing is going to be happening here when we are considering information, how much fast information can travel. So if the warp drive experiences the same effect with light, then there is no way to send a message in front of the spaceship. So in that sense, for the pilot, will be very difficult to send a signal in front of the spaceship to say, I want to change the route, or I want to move left, or I want to move right, or something like that. Instead, what we are going to have at maximum is that the path of the spaceship is going to be preset even before the trip had started. So I suppose that's really bad news for Captain Kirk. Maybe he will have to find another job. All right. Are there other possibilities that we haven't thought about? Are there other ways to make interstellar travel possible or faster than light spaceships? Well, in quantum mechanics, we have what we call the quantum entanglement. Let's say that we have two particles that have a particular state, but we do not know the state. But we put them at very different distances. They are still entangled. So what is going to happen is that at some point I observe one of the states of one particle. I will immediately understand what is the state of the other particle no matter how far it is. So in some sense, you would think about, well, I can obtain information by looking at one particle from a different particle that is very far away. So this, of course, is giving rise to a lot of discussion, a lot of paradoxes, a lot of information discussion in the world. So this is still kind of unclear how this quantum entanglement is kind of working. But the question here is, well, maybe one day we really understand how it works, and we would be able to use it to actually send information faster than light. And could we use this to actually travel faster than light? We don't know yet, but it is a possibility. Another crazy possibility, of course, in the far distant future is we know what is the speed of light. We may know why the speed of light is what it is. And in the future, maybe we can actually play with the properties of the space-time or the quantum form that makes the space-time itself. Or we may find a way to change the speed of light. If we can do so, then we can say we cannot travel faster than the speed of light, but we can make the speed of light much, much higher. If we can make the speed of light infinite, then traveling below the speed of light still means we can travel at any speed we want. It may be a possibility. Why not? Or we may find new physics that are telling us new ways or new methods that we currently cannot even think about, that will give us new options and new ideas for interstellar travel. Who knows? So please keep tuned in and let's find out together the new discoveries in science and new discoveries in fundamental physics to find out how we can really reach this in the future. So my conclusions would be, we have already made giant steps in traveling faster and faster. Interstellar travel is already there, as I mentioned, with Voyager or the New Horizons. It's just a matter of being practical. If we're thinking about the near future, what is going to happen in the next decades or something like that, we think subluminal interstellar travel is almost already there. We are really close to actually be able to send a person to the nearest star. But the future is becoming more and more exciting because we are really thinking what are the basics, what are the science part, what we can do with wormholes and space drives. So what today is science fiction, tomorrow, very soon, could be actually real science. Long time ago, people could consider traveling, let's say, hundreds of kilometers in a day something really crazy, something that it will never be possible. Today we can take a weekend trip to Korea, to Japan, to Philippines. We can just take a flight on Friday evening and come back and work for Saturday or Sunday or Monday. What in the past was considered as something crazy, we can do it today. So the same thing, maybe today's ideas are going to be crazy, but next time we can really travel to Alpha Centauri for the weekend. So with this, thank you very much, and thank you for your attention.
Thank you, Dr. Juan Carlos, for the amazing speech. Continuing for our Q&A session, our first question is, would decelerating it from a relative high speed to the speed of it to be safe enough to safely land the spaceship? If no, why? If yes, then why? Will it be hard as accelerating in it the first place? And how, actually?
Mm-hmm. Well, you'll have to think that accelerating and decelerating are basically the same thing. The only thing that is changing is in which direction you are putting the force. So, of course, if we have problems about accelerating some spacecraft or spaceship, we are going to have the same issues when we want to decelerate it. What we cannot do is launching something and accelerating at very high speeds and then expecting that it will just land gracefully on the surface of a new planet. We have to decelerate, and in general, it's going to take as much time and as much effort as everything that we have been using for accelerating it. In the case of solar sails or nuclear reactions, it will take like days to accelerate something. When we are reaching destination, of course, if we want to land safe enough, we have to start decelerating also many days in advance. So, of course, when you're thinking about this interstellar travel, you have to sum to this in these kind of cases how much time you need to accelerate and how much time you need to decelerate. Because obviously you need to reach from very fast velocities to zero, and you want to do this in a proper way. You cannot accelerate immediately because, of course, if you feel decelerations on your body, a deceleration of few gravities is okay, but as long as you go to decelerations of 5G or 7G, astronauts notice very well. The body can still can already feel its effect, and we don't want this to happen. We want to have decelerations that are smooth for the human body. So even if we can accelerate very quick with nuclear reactors, we still want to make it safe for the bodies. Of course, once we are talking about playing with space-time, then it's not really that we are going to be accelerating or decelerating. It is going to be the space-time itself, the one that is bubbling. So, of course, this is going to be a very different discussion altogether, and we are not going to be limited by this.
That's quite interesting, Dr. Juan. For the next question, what happens to information entropy of a system, say a quantum particle, when it transits a wormhole? Since bigger system or space traveler are essentially multi-particle systems.
That's an interesting question, and I would say so far it's very open because what we can understand now is to the quantum level. So, in principle, when we transverse what we understand so far, a black hole or a wormhole, is that we are going to have a problem with the information. And this is a very nice topic that came up with Stephen Hawking. And that's what we call the information paradox, right? And this is something that we still don't understand. There may be some people thinking that the information is destroyed on a black hole and there is no way to recover it. Other people would say that we can recover somehow via some radiation processes like Hawking radiation. Some other people is still skeptical about this. And of course, we have to think about what is the meaning when we go from quantum scales to large scale, like thinking about what is the meaning when we want to just get a human going through a wormhole. So this is still a large discussion. And the big idea that we can consider here is that when we are thinking about wormholes, in principle, the horizon that we have in typical black holes is not really going to be that constraining there. And we are not going to be destroying the information. We are not going to be trapping whatever passes through immediately. This is going to be smoothly traveling through the throat of the wormhole. So in principle, one of the options may be that information is not going to be such a big deal when we are thinking about wormholes. Of course, as I mentioned, this is still a topic of huge debate, huge discussion. And it's very probable that if you want to look about this, every single week you will find new articles and new scientific papers discussing about it. It's still very unclear what can happen with this.
About that, people want to know, where does this what you call wormholes connected to?
So Is there an idea of asking, okay, I see something that looks like a black hole. How do I know if this is a black hole and I'm going to get sucked in the horizon and then I will be trapped, I will disappear? Or is it a wormhole and then I can travel safely? I suppose this is the kind of question like, how do we know it's a wormhole I can transverse or is something else that would kill me? I suppose the question is in this direction. So far, of course, what we see through the throat of the wormhole is going to be a bit different. When we are looking at a black hole, we are going to be seeing how the matter is slowly going there ab infinitum, and from our point of view, it will never reach what we call the horizon. Whereas if we are approaching a wormhole, what we're going to be seeing when we approach it is the throat, and we can see all the material and the particles that are going through it. Of course, we will not really see this kind of a hard horizon that we can see in the black holes. So this would be a way to distinguish if this is a killer black hole or a transverse or a killer wormhole or a transversable wormhole. Of course, I would say in principle, by nature, it would be very difficult to figure out these things out unless we do many experiments. But maybe one day we can make the technology to create those ourselves. And maybe we can just put the proper constraints so that we know that the wormhole we created is safe. Just by looking, knowing the parameters and looking at what is the aspect it has.
Okay, that was rather interesting too. Another interesting question from the crowd about light sail. What is the status of the Breakthrough Starshot initiative to use a laser-driven nanocraft fleet to Promina B in Alpha Centauri, championed by Yuri Miller herself?
Okay. All right. I knew that there are incentives about this. Like basically, instead of using a solar light, using the photons I was discussing, we could actually use lasers. So in some sense, even if we don't have light, we are carrying our own light for our sail. But other than that, actually, I have to be honest here, and I have to say that I am not aware about the latest status or latest updates for this particular project. So I'm afraid that for this question in particular, I cannot give it. I cannot provide the details. So sorry about this particular question.
It's fine. It's actually from our Professor CP. So continuing to our next question. One of the perspective of interstellar travel, scientists have the idea of refueling at checkpoints such as moons, asteroids, and comets. What is your view on the practicality of mining fuel on these celestial bodies?
This is indeed one of the options because, as we were discussing at the beginning, one of the problems that we have when we are discussing about chemical reactions using fuels, liquid and solid fuels, is that we have to store them, and this is creating a weight that we also have to lift. A possibility would be we don't put all the material that we need. What we do is we just fill it a particular percentage, and then we can refuel in other points. Like it would be very similar to what we have now with cars or motorbikes. We don't need to fill the car so that we will use the car until the car breaks. But I would say it is going to be interesting as a first stage, but it is perfectly possible that we can get the material we need, although it would be kind of tricky how to do this. There are also other ways, like thinking about if we travel through space, we can actually get hydrogen. We know there is plenty of hydrogen in the interstellar space because we can detect it with our telescopes. One of the questions would be how much fuel we can get. And there is very little per square meter, so we will need a lot of time to collect a proper amount. But of course, if we go to moons, asteroids, we can actually get the material. Again, how much we can get it's a different story, but it is perfectly possible. In terms of practicality, I would say that we are here discussing burning the chemical reactions, and I said this is going to be very inefficient. So my feeling on this, or my 2 cents, and this is personal opinion, would be that by the time we know how to refuel or do these kind of ideas, we will not really have the technology to use the ion engines or to use the nuclear reactor engines. So those are going to be much more efficient than actually going to different points and refueling them. Of course, if we can have both technologies, or we can combine both technologies, similar to having a hybrid car now, both with fuel and electricity, would be kind of a possible idea. So why not checking both ideas? But as I said, my personal feeling is that I think we will be going in a different direction, where our fuels are going to be a lot more efficient than, and this will not really be that much necessary.
Okay, thank you, Doctor. So our next question. When do you think this kind of travel will be possible? Is it possible with today's knowledge, or we need new physics to make it more a reality?
Mm-hmm. Well, as I mentioned at the beginning of the talk, we are already traveling. Like, we already have the Voyagers that are traveling to different stars. So it's already on the way. Question, of course, I suppose, is when we can put a human and actually make this human travel to a different star, which, of course, will take a lot of time. I would say we have the technology here. There is a test even with the solar sails. There are tests with some of the methodologies, the ion thruster. So I would say, of course, it will take time. Let's consider several decades, so that the engines are going to be a perfection. And once we have the technology, as I said before, it's not only a matter of the physics and the engineering, it's also a matter of the economy. So at some point, we will have we will be ready as humans to be able to do the first trip to a different star. The question that we are going to ask is it worth it? And of course, this is going to take, I would say, a lot more time to figure it out. And for my personal feeling, this is what is going to be delaying most our first trip to Proxima Centauri. But I would give it like probably a few decades. Is going to be optimistic, but we are talking on the orders of a century here. So maybe we are not going to see it, but let's try to be optimistic. Maybe our grandchildren or our grand-grandchildren will be able to see it. Who knows? Like, you know how this is evolving. We know that we are in a time in which technology is evolving exponentially, and we never know what is going to happen. So now I'm mentioning about centuries. Many of my friends actually mentioned that we would never have the technology in this generation to take a picture of a black hole, and we have done it ourselves. So when I say we don't have the technology now, we will have to wait for centuries for interstellar travel. Who knows? Maybe Elon Musk does something amazing, then the company keeps going on, and like in the next couple of decades, we have something there. We don't know. So let's be optimistic and figure out how this is going to work. I'm really excited about these sort of things myself.
Okay, thank you once again, Dr. Juan Carlos. This concludes our Q&A session. Thank you for answering this very inspiring question. So, for your information, this session is recorded and will be available for you guys to see later. Participants, please be reminded that the QR code for attendance will be available at the end of the session. Okay, so it has been a long morning, right guys? Now let's take a break. We'll be back at 2:30 p.m. Stay tuned for the next speaker, Dr. Kuhan Chandru. Thank you.